In this lesson, we'll cover derivatives of logarithms and trigonometric functions. To start with, let's do a quick review of some properties of logarithms. First of all, if you see y is equal to log base b of x, this is the inverse of b to the x. And specifically, this means if you compose them, they cancel each other. So first, if you see log base b of b to the a, log base b and b to the a are inverses, so this actually simplifies nicely to a. And likewise, if you see b to the log base b of a, this is equal to a as well. Now, what is the reason for this? Let's just look at a couple of quick examples. For example, what is log base 5 of 25? What's that equal to? This question is asking, if you take the base, which is 5, what number do you put into its exponent so you get 25 back? And well, the answer is 2. Log base 5 of 25 is the same thing as 2. To make this very obvious, you can write this as log base 5 of 5 squared. Here, log base 5 and 5 cancel, and it leaves you with what's in the exponent, which is 2. Likewise, maybe just another one. What is log base 2 of 16? What does that equal? This question is asking, if you take the base, which is 2, what number do you put in the exponent to get 16 back? And the answer is 4. To make this obvious, you can say, well, log base 2 of 2 to the 4th is equal to what? Well, log base 2 and 2 cancel because they're inverses, and it leaves you with 4 left over. These rules are very abstract, but this is what they're trying to convey. Maybe one more thing to note. We're mostly going to work with the natural log in this class, and for this reason, these two rules can be expressed not with log base b, but as a natural log. For example, the natural log of e to any power is equal to that power. Here, these two functions are inverses, and so they cancel. Likewise, e to the natural log of anything is also equal to that anything, a. Let's try using these ideas in the next example. In example 1, we have a graph of the natural log of x. I would like to determine a formula for this function. That is, can we find y prime? First, let's think about what the derivative actually looks like. I'll note that the natural log, y equals the natural log of x, is always increasing. And this means the derivative is always positive. So it's always here. It is never 0 and it's never negative. Furthermore, here, the slope of the tangent lines are very large. So I know the derivative is going to be large over here. But then over here, the tangent lines are smaller. So therefore, the actual number for the slope is going to be small as well. So I'm expecting a graph that is positive. It's big over here and it's smaller over here. Now, how do we go about finding the formula for this thing? We're actually going to derive it. So we're told that y is equal to the natural log of x. We can't take the derivative of this equation because we don't have a rule for the derivative of the natural log. But there's a trick that we can do. We can exponentiate both sides. That is, put e to the power of both sides in our equation. On the left, we have e to the y. What do we have on the right? Well, we have e composed with this inverse, which cancel to give us just x. So the original equation, just to jot it down again, was y is equal to the natural log of x. I did the same thing to both sides of this equation, which was exponentiate it, and I simplified this side. I cannot differentiate this, but I can take the derivative of this equation by using implicit differentiation. So that's my next step. I'm going to take the derivative of both sides with respect to x. Taking the derivative of the left side gives us e to the y, but we have to multiply by the derivative of y, which is y prime. That's exactly the thing that we're solving for. On the right, the derivative of x with respect to x is 1. Our goal was to find y prime. It is right here. I can divide this to the other side. We have y prime is equal to, this is 1 over e to the y. And that's my formula. Now, it would be nice if it was written in terms of x's, and this is a very easy thing to do. If y is equal to the natural log of x, and we put the natural log of x here, this is what we get. We get that y prime is equal to 1 over e to the natural log of x, but e to the natural log are inverses, and so the whole thing reduces to simply 1 over x. So I can now state our formula. What is the derivative of the natural log of x? It is 1 over x. So we'll add this to our list of formulas. Now, this is the function for the derivative. Does that compare with what we expected the graph to look like? And the answer is yes. If you graph 1 over x, it looks something like this. It starts out large, and then it becomes small when we go in this direction, and it is always positive. Before moving on, I'd like to add on also that you can generalize this to the derivative of a logarithm of any base, and the formula is very similar. It's 1 over x, but now we have to multiply by the natural log of the base, which is b. So in general, if you encounter a logarithm, if you have a natural log, the formula is very simple. It's 1 over x. We proved that. But if you have log of some other base, it still is 1 over x, but you have to divide by the natural log of the base to complete the derivative. In example 2, let's practice these rules by taking derivatives involving logarithms. So in part A, what is the derivative of the natural log of sine of x with respect to x? Well, we have to use the chain rule here because we have a composition of two functions. First, the log goes to 1 over what's ever composed in the function, which is sine. But by the chain rule, we have to multiply by the derivative of sine, which is cosine. And unsimplified, this is the answer. However, you can write this as cosine of x over sine of x. And by definition, cosine over sine is cotangent. So we could leave it like that, but this answer is fine too if you're leaving things unsimplified. Now, what about the derivative of log base 2 of 5 minus 7x? Well, for this one, the rule is if we're using the chain rule, we have 1 over what is composed in the function, which is 5 minus 7x. But here we have to multiply by the natural log of the base, which is the natural log of 2. The last thing to do is multiply by what's composed, the derivative of what's composed in the function, and 5 minus 7x has a derivative of negative 7, and unsimplified, that's the answer too. Now what about in this last one, the natural log of just negative x? Here we still have a composition, but what happens here? So I'll mark the composition, and to take the derivative, we get 1 over negative x. But by the chain rule, you have to multiply by negative 1. You can put this into one fraction. This is negative 1 over negative x. And those negatives cancel to give you just simply 1 over x. So what's the derivative of the natural log of negative x? It's 1 over x, which is the same thing as the derivative of just the natural log of x, whether it's negative or positive. I'll note that the absolute value of x is plus or minus x depending on the numbers that you're putting in place of x. And for this reason, we actually have another derivative rule, or a more general one. If you take the derivative of the natural log of the absolute value of x, the answer is also 1 over x. And the reason is, if it's positive x, you get 1 over x, and if it's negative x, you also get 1 over x. So it doesn't matter which one that you use, the derivative is always the same. All right, but let's try a more complicated derivative. So here's the derivative of the natural log of this mess, a fraction with a square root, and there's a product with this power in the top. I mean, this looks like it could be a very difficult derivative to evaluate. But it turns out that logarithms have some properties that are useful here. For example, maybe you recall that if you look at the natural log of a product, how can you rewrite this as a sum? Well, in fact, it's equal to the natural log of A plus the natural log of B. There is also a rule for taking a log of A divided by B. Here you don't add them, but you subtract log A minus log B. And one final rule is, if you have log of some expression to a power, you can bring that power to the front of the function. So this power P can be brought down here. So here are 3 very important properties of logarithms. And in fact, they can make taking the derivative of this thing much easier. Before we even take the derivative, I'm going to take this mess of an expression and I'm going to simplify it by using these three properties. And I'll write the denominator as x minus 2 to the 1/2. To start with, there's a fraction. And using the second property here, if I call the top a and the bottom b, I can write this as the natural log of x plus 1 cubed times x plus 2 minus the natural log of x minus 2 to the 1/2. Now, here we have a product, and I can use this property to express this as a sum. So this is the natural log of x plus 1 cubed plus the natural log of x plus 2. And I still have minus the natural log of x minus 2 to the 1/2. And lastly, we have these exponents that we can remove and put in the front of the expression. So we get 3, the natural log of x plus 1, plus the natural log of x plus 2, minus 1/2, the natural log of x minus 2. No derivatives occurred between here and here. I just simplified this expression to this one. This is very difficult to take the derivative of, but this one will be very easy. So I won't differentiate this. I'll differentiate this equivalent expression. So we are taking the derivative of this whole thing, 3 ln x plus 1 plus 2 ln x plus 2 minus 1/2 ln x minus 2. Note that with a little practice, it's very easy to take something like this and quickly write it down like this. We can go through term by term and take the derivative. Starting here, what's the derivative of 3, the natural log of x plus 1? Well, it's 3 times 1 over x plus 1. Here you don't have to really use the chain rule because the derivative of the inside is just 1. The same thing will happen here and here. Next we get 1 over x plus 2. Then we have minus 1/2, 1 over x minus 2. So this would be a very long derivative to take. This, very simple. We can basically do it in 3 steps, and that's the final answer. In example 4, we're going to take the derivatives of these functions, but notice that there are no logarithms in either of these problems. Even though there aren't any, they will actually help us get our answers. Let me show you what I mean. What is the derivative of y is equal to x to the x? Now, it might be tempting to look at this problem and say, oh, well, we have a rule for this. The derivative of x to any power is n times x to the n minus 1. But this is only valid if n is a number. So the answer to this problem is not bring down the x, copy down the x, and subtract 1 from the exponent. This does not fall into this category because this exponent is a variable and not a number. Likewise, you can't use this rule to solve it either, where if you have some number to a power, it's a to the x times the natural log of a. This also does not work. And the reason is here the base is a number and here the base is a variable. So unfortunately, these don't work. So what do you do in this case since it doesn't look like we have a rule to help us solve this? The trick is take the natural log of both sides. We're going to do something called logarithmic differentiation. If these two things are equal, then these two things are equal. But on this side, we have a property of logarithms that says you can bring this x down front, changing this question to take the derivative of the natural log of y equaling x times the natural log of x. Here, now we can actually take the derivative of this expression because this side is a product and we can use the product rule. But what about the derivative of this side? What is the derivative of the natural log of y? Well, we have a rule for the natural log. It's 1 over what's ever composed in the function. But by the chain rule, we have to multiply by y prime, the derivative of what's composed inside the function. Essentially, we are using implicit differentiation here. On the other side, I can use the product rule, which is the derivative of the first times the second plus the first times the derivative of the second. And we're basically done. The goal was find y prime. I'm going to multiply this y to the other side of my equation, and I'll write my answer like this. Y prime is equal to y times, I'll put the natural log of x plus 1. So I took this y, I multiplied it to the whole side of this equation. This I just wrote as the natural log of x, and x times 1 over x is the same thing as 1. To complete this problem, I only want x's on this side of my equation, but y is the same thing as x to the x. I'll just plug this in here. Running out of room, but here's the answer. Y prime is equal to x to the x times the natural log of x plus 1. So this is the answer to part A. Now, what about part B? You could take the derivative of this equation without using any type of logarithms. However, if you took the log of this side, it would simplify the equation very nicely. So before taking derivatives, I'm going to take the natural log of both sides and then simplify this whole expression. So here's what I'm doing. It's the natural log of y is equal to the natural log of, and I'll write this as x to the fourth. I'll put x minus 4 to the 1/2, all divided by 2x plus 1 cubed. Now, on the left side, it still is the natural log of y, but how can I break apart the right-hand side? Let's actually try to do this in one step. It's going to be log this minus log this. I can split this into the sum of two logarithms and then pull the exponents down front. The answer is, it's going to be 4 log x plus 1/2 log x minus 4 minus 3 log 2x plus 1. You can get from here to here in several steps, but I'll just note that, well, we have this fraction, which means it's the top minus the bottom. In the bottom, you could bring the 3 down front. In the top, there's a product which goes to a sum. And in both the sums, you can put the exponents in front. This and this are equivalent, but I'll take the derivative of this equation because it's easier than taking the derivative of this. On the left, the derivative of the natural log of y is 1 over y times y prime. And on the right, we get 4 over x plus 1/2 1 over x minus 4 minus 3 times 1 over 2x plus 1 times 2, where this 2 came from the chain rule, the derivative of this thing. To get our final answer, I'm going to multiply the y to this side. Now, y is equal to this, so I'm simply going to take this and place it here, and this stuff in parentheses. This is my final answer. Y prime is equal to x to the fourth root x minus 4 all over 2x plus 1 cubed times 4 over x minus 1/2 times 1 over x minus 4, and I'll put minus 6 over 2x plus 1. Now, without this trick, getting to this final answer could take a very long time, but here, this process is actually pretty quick. In the last part of the section, I simply just want to introduce the rules for arctangent and arcsine. So we won't derive them, I just will simply state them and we'll try them in a couple of examples. If you see arctangent or tangent inverse, this is referring to the inverse of the tangent function. And when you take its derivative, you get 1 over 1 plus x squared. Over here, if you see arcsine or sine inverse, we're talking about the inverse of the sine function. And when you take its derivative, it reduces to 1 divided by the square root of x minus 1 squared. Let's use those in example 5. What is the derivative of arctangent of the natural log of x? I'll use this rule here. Notice that instead of x, we have the natural log. So we have a composition. The derivative is 1 over 1 plus whatever is composed in the function squared, which in this case is the natural log. Now by the chain rule, you have to multiply by the derivative of the natural log, which is 1 over x. In the second problem, we have sine inverse of 3x plus 2. to take its derivative, we have to use this rule here, which means we'll get this, but instead of x, we'll have 3x plus 2. Often, it really does not help to square this out, so I'll leave it just like this. But by the chain rule, I have to multiply by the derivative of 3x plus 2, which is simply 3. So unsimplified, these are the derivatives of these functions. Let's look at a proof of the derivative of arctangent of x. Why does it equal 1 over 1 plus x squared? For this problem, I'm going to note a couple of things. For starters, if you take tangent and you compose it with arctangent of anything, it's going to be equal to that thing, that anything. And the reason is, if you compose tangent and arctangent, they're inverses, and they cancel each other. Another important identity is, if you see 1 plus tangent squared of anything, that's the same thing as secant squared of that thing. I think that's pretty much all we will need to solve this problem. So y is equal to arctangent of x. And I want to find y prime. But I can't do that by taking the derivative of this equation. But what I can do is take tangent of both sides. Why does that help? Well, it doesn't really help on the left. We get tangent of y. But tangent composed with arctangent cancel to give us, in this case, just x. I can't take the derivative of this, but I can use implicit differentiation to take the derivative of both sides of this. So what I'm going to do is take the derivative with respect to x of both sides. The derivative of tangent is secant squared of y, and by the chain rule, I multiply by y prime. Y prime is exactly the thing that we're looking for. The derivative of x is 1. If you solve for the derivative, it's 1 over secant squared of y. And hey, we did it. That's the formula for the derivative. However, I'm going to replace secant squared of y with 1 plus tangent squared of y. So y prime is equal to 1 divided by 1 plus tangent squared of y. Ultimately, I'm trying to get to this thing here, which is in terms of x. Now, y is the same thing as arctangent of x. Let's go ahead and plug that in. Y prime is equal to 1 divided by 1 plus, and what this really is tangent of arctangent of x squared. As we've noted, tangent composed with arctangent leave us with just, in this case, x. So I get 1 over 1 plus x, which is squared, and this is where the formula for the derivative comes from. You can use a similar idea to prove the one for arcsine as well, but I'll leave it at that for this problem.